Hello everyone, nice to see you again. I hope you have a wonderful week. Okay, I know many changes have occurred recently due to the reopening, and there are uncertainty about all those assessments and other things, right? So today we will go through another chapters, but this chapter we will mainly focus on the discussions of those applications, okay, rather than the theoretical part of it. So before we move on, as I mentioned, we will discuss about the assessments, right? So as you can see, I have updated the assessment weightage, okay, whereas I have deleted the tutorials 20%, okay. This is the decisions made due to the compliance to the EAC. All right, so we have discussed with the EAC, and actually we have decided to do not change any weightage, okay, that exist, okay, in our course, okay, except the final exam. Okay, so it is how we going to replace the final exam. So therefore all the 40% of the final exam will be now transferred to the test. All right, so the test will be home based. Okay, it likely will be synchronous online, meaning to say we will set a time, and we will run it at the same time and end at the same time. All right, so for those who do not have the connections, so make sure you contact me as soon as possible. So far I've seen 3 names, okay, listed here, all right, that haven't go into the Google Classroom. Okay, so if you have their contact, do let them know, all right, about this, and so that they can contact me as soon as possible to discuss how we can run it. Okay, especially maybe for them with a special case, okay, they will do it in a different way or what. All right, so now we move into this sections, right, about the heat transfer related applications, right? And before we start, I just give you these 2 links, okay, where you can find the benchmark guide used in Abacus. All right, so again, this is part of the Abacus menu. All right, I believe other commercial software, they do have this benchmark. correct, where they actually did their analysis and compare it with the a certain experiments, okay, to ensure that their software, the algorithm or the code behind the software are actually correct, okay, is validated. Okay, so this is the process that even a software company need to do, right? That's why they have this benchmark guide where how they do it, and you can try to repeat it, okay, according to their benchmark. All right. Then also there is this, I found online materials from UTM, all right, so you can check their content as well, okay, and you can see how far we are, okay, with theirs, or how in front of us, okay, or how it is. All right, so just to compare between ours and theirs. All right, so you can always refer to theirs if you want, right, because the basic principles are very similar, right? So now we will just quickly go through the principle behind the finite element methods, right? So basically, finite element methods are solving differential equations and integrations, right? So there are many differential equations that we need to solve, okay, simultaneously, all right, to yield solutions to our problem, okay, just like you are solving by hand, but then now we discretize them into many but small problem, okay. So mathematically, finite element methods can be developed for various fields, okay. As you have seen previously, we have derived mainly for the structural, okay, but we can always use the same concept to apply it for different applications. As you can see in the heat conductions field, or the fluid flow field, as well as electrical and acoustic, their differential equations are very similar, okay. They are two parts, okay, x, y, or maybe in the three-dimensional there are z axis as well, okay, plus constant, right, plus a constant, okay, equals to something, right? So the variables, the only difference are the variables and the parameter, okay. For example, here for the heat conductions, our variable will be the temperature, okay, just like in the structural, our variable will be the displacement. So when we start to derive for our elements equations, we will use the displacement function, okay, to form the equations for each of the elements, okay. So similarly for different applications, when we deal with heat, then the variable will be temperature, okay. So this will be the basic parameters that we will get, okay, to analyze further, okay. Then the parameters that we need to input will be the thermal conductivity and other things, okay, whereas we can also include several different boundary conditions, okay. Similar to the flow, we have stream as a variable, electrical potential using U, okay, into our equations, and for the acoustic will be the pressure, okay. So the equations will be very similar, all right. So now in order for us to start, we just go through one derivations, okay, or maybe an idea of how we get that equations, okay. So for heat transfer related applications, we will have this conductions, okay. So we will start with the conduction because most of the heat will be transferred through conductions, all right. So here when we start to derive, okay, let's consider one-dimensional heat conductions, okay, the easiest one, only along one directions, okay. Then to derive this, at start we don't consider any convection first, all right. So just only conduction, no other heat loss except conductions, all right. So now what we will do is we will see we will form a control volume, okay. So this block would be our elements, okay, in a three-dimensional case, okay. So if you want for one-dimensional, it will be just a line or yeah, just align elements. All right, so the control volume will be the energy in to the element plus whatever generated. Okay, so the generated energy could be additional energy that you add to the system, or internally it's generated. Okay, it can be generated inside. Okay, if this is maybe a electric coil, okay, then it will generate the heat by itself. Okay, so it can be generated inside, should be equals to what are the output, okay, the E out, the energy out, plus whatever store inside. Okay, the energy store in the element itself. Okay, so whatever we enter and the output, okay, whatever when it minus out, then it will become the generated part and also whatever energy store. So in the heat transfer problem, the energy will be stored in terms of heat. Okay, therefore you will see the temperature increase. Okay, when you remove the energy in and out, then this energy store will now slowly change again. Right, so there is this storage part, okay, in the equations. Okay, so if we form into a more detailed equations, then this will be given as such. All right, so whereas you can see that the energy in will be the heat flux. Okay, heat flux referring to the amount of energy per area. So if you have this area, okay, the heat flux multiplied by the area, okay, the area itself, it will give you the energy that is being input to the control volume. Right, similar to the other side. Okay, when it's go out. Okay, whereas this distance can be a dx, okay, a very small distance, depending on our mesh size. Okay, then the Q, okay, the capital Q will be the internal heat source. Okay, if it is generated inside. All right, inside the element, whereas the T is the time and the A is the cross-sectional area, okay, where the flow is being transferred along. Okay, so now when we apply that, okay, to obtain the heat flux, then we will apply the Fourier law of heat conductions. Okay, so this is the basic equations. I believe you have learned this in heat transfer course. All right, whereas it's minus k dt over dx. Okay, the x is the distance, okay, where across the element itself. Right, so we will see that this will be the temperature gradient. Okay, so here we would in these equations we would see that the minus signs occurs here. Okay, as the temperature over here is usually higher than the other side. All right, so there will be a heat flow with positive in the directions opposite to the directions of the temperature increase. Right, so now to further obtain the heat flux on the other side, okay, after a certain distance, okay, dx, then we will note as qx plus dx. Okay, so everything similar, but then this part when we want to differentiate respect to x, where the x will be x plus dx, therefore we could apply the Taylor series expansions, okay, given as such. Okay, but in most case when we try to solve for it, we would take the first two terms, okay, and neglect the others. All right, okay, because these terms will be getting smaller and smaller, okay, and eventually become zero. Okay, therefore in most cases when we come to our programs, okay, or when we come to our calculations, we would want to maybe take the first two terms, okay, or the highest maybe up to 3 terms, up to depends on what applications you are dealing with. Okay, usually just the first 2 terms will be very sufficient. Okay, So once we take the first two terms, what we do will be, when we differentiate respect to the x, okay, plus dx, therefore we would get this would be our functions, okay. So this would be our functions itself. So our functions remain, okay, dt over dx plus d our function, okay, respect to dx. So d our function itself, okay, oh sorry, our functions include the k, alright. So d our functions over dx multiplied by dx, okay. So this is how we get the heat flux after a certain distance, okay, a small distance itself, right. Then whatever left, okay, in and out may not be the same, okay, meaning to say something missing, okay, and that something may be being lost or being stored, okay. But then in our control systems now, we don't consider losses, okay, we don't have convections and radiations or whatever it is. Therefore whatever changes will be stored inside the element itself, okay. Therefore this energy stored would be the delta U, okay, which you are very familiar since maybe secondary schools, okay, whereas you have specific C, okay, the mass, and delta T, okay. You can see that mc delta T, right. So it is the amount of energy being stored in the object, or now because we are talking about the elements, now is the energy stored within the element itself, right. So C and the mass, we can get it based on the density multiplied by the area and the distance, okay. So this area multiplied by distance give us the volume of the whole elements, okay, and the dt, right, the changes of the temperature. So this would be mc delta T, right. So it's the same equations because the law is still remain unchanged, right. So now what we can do now, we just apply it to our equations. Again, this is only one-dimensional heat conduction equations. We just plug them in, okay. So you have rho c delta T over the time, right, and the other side will be only about the x, okay. So you will also see that this k, the k is the thermal conductivity. We put xx, meaning to say here we would only consider the thermal conductivity along the x directions, okay. In some cases, in three-dimensional cases, okay, the heat transfer rate or the thermal conductivity in x and y and z directions may differ, okay. So therefore in this case, to be safe, we will just take into the differentiation itself, okay, for a general in a general form, okay. When our case is a steady state, okay, then therefore the differentiations respect to time will give us 0, okay. So differentiate respect to time, this part becomes 0, okay, meaning to say when it is steady state, there would be no change in terms of the energy stored in the element itself, okay, because in and out will now become steady, okay. Whatever stored should be stored there and doesn't change anymore, alright, with respect to time, therefore equals to 0, okay. But then when we deal with cases where as I mentioned, if the thermal conductivity now is also a constant, then therefore we would get this equation, the simplified equations, alright. So these equations is assuming that the thermal conductivity do not change respect to the distance, as well as do not change respect to the temperature, alright. So I would detail more on when the thermal conductivity will change according to temperature, right. So that would be the basic of the heat transfer equations, okay, being used or being applied in the finite element methods, okay. Those derivations are very similar to what you have learned in the heat transfer cases, alright. if you want to see more derivations on the three-dimensional cases, you may get this text. All right, it's very useful and popular text. Okay, very comprehensive, incorporals, written by Professor Corpras. Right, and for a heat transfer problem itself, we could separate them into three type of boundary conditions. The first one, the Dirichlet's boundary conditions. The second one, Newman's, and the third one, Robin's. Right. So, what are the difference? Okay, is that the definitions? These are the mathematical form of the boundary conditions. Okay, there are mathematics, all right, behind it. So the Dirichlet's boundary condition actually referring to the constant surface temperature, meaning to say we would have an element and we would want to set this surface to be a certain temperature TB, okay, and the temperature will not change. Okay, we would give other heat flux or heat input towards there, but on this phase we attach it to a certain temperature. Okay, that's why we would have a constant surface temperature at one boundary surface, right? So this, in this case, we will apply this Dirichlet's boundary conditions mathematically, right, in the equations. So in the software, the FEM software itself, what they do, they will also apply based on this Dirichlet's boundary conditions. Okay, so when you see this term Dirichlet's boundary conditions, you don't get scared. All right, it's just referring to this kind of conditions. All right, then for a Newman's boundary condition, similarly, the second type of boundary condition, it's referring to the heat flux itself. Okay, the heat flux. Okay, so you will have a Q1 here, a Q2 here. Okay, the heat being input into the system itself, okay, are a constant. Okay, so in that case, we would apply a what we call a Newman boundary conditions. It depends on whether it is a constant surface flux, or in other case it is insulated. Okay, when it is insulated, meaning to say there is no heat flux. Okay, this equals to 0. Okay, when it is insulated, no heat transfer in and out through this surface. Okay, again, this is 0 is still a constant, so they would still consider as a Newman boundary condition, whether it is a number, a constant number, or a constant 0, right? So it's still a Newman boundary conditions. Okay, the third type will be the convective surface conditions, Robin boundary conditions, where they would apply a constant, okay, H, which would be the convections coefficients. Okay, convection coefficients, okay, H. Okay, and it change according to the temperature difference between the elements. Okay, in this case, again, the temperature is being assigned or computed at the node. Okay, similar to the displacement. All right, so therefore this temperature referring the temperature of the node. Okay, comparing to the ambient temperature. Okay, what is outside. Okay, so there would be a convection. So if this is the outside one, it could be referring to, if it is a forced convection, it would be referring to the temperature of the air, okay, being forced to the system. Okay, so we will have the Newton law of cooling, the QH equals to H with the temperature difference between the node and the ambient, right? Similarly, some software, they do include radiations, okay, in their cases. Okay, but if in case the software doesn't include that, we can also treat that as a kind of convective surface radiation. Okay, because it depends on the changes of the temperature, okay, difference of the temperature at the node comparing to the ambient. Okay, so how we would apply that is in the radiation type. Okay, there is a Stephen Boltzmann law of radiations apply, okay, given by this. I think this is wrong, this should be minus. All right, okay. So therefore from this we can always break them into two parts, okay. This can be break into t square plus t infinity square, then t square minus t square t infinity square. Right, then again the second order part we can break them into two. So you can see that this constant, okay, will be the h value. Right, so we can apply this technique into our finite element software, okay, to treat as the radiations. All right, so you may need to make sure that your units are consistent, okay, according to the software. All right, so this is what given in the textbook, right? And if you apply it using software, okay, then you have to check their conversion table, right? So this is from the Abacus, and I have also shared the conversion table or the units used in LISA FEA, right? So you can always check on that note as well, right? Then for the thermal conductivity would be our main input, right? So what we do when we try to apply a thermal conductivity for our analysis, make sure it is reasonable, okay? So whenever we select any values, it should be reasonable, okay? This is a stage where you have to jump out from your comfort zone, okay? Previously, when you are dealing with problem, okay, most of the time all these values are given, okay. You are given k equals to certain numbers, okay, you are given Poisson ratio equals to certain numbers, and so on, okay. But in real case, you have to decide, okay, what is all these values. They are not given, all right. So in that case, you have to search for the reference, okay. What are the experiments or past papers or whatever it is that has tests or validate a certain values, okay, for maybe a solid, okay, or a fluid or whatever it is, okay. So you can always get this from papers, okay, from textbooks, okay, your heat transfer textbooks, okay. Whereas behind that there are few important tables, okay. If you can see, those tables are created, okay, with a reference, okay. Those reference are a test, a result from certain laboratory, and so on, okay. So you can always select based on that, all right, not based on whatever values you want, okay. So also you can see that in here they would mention aluminium 0 degrees Celsius, okay, steel 0 degrees Celsius, meaning to say the thermal conductivity when they do the test, this is the test temperature, right? So you can always find what are the other thermal conductivity for a certain materials, okay, at a certain temperature, okay, meaning to say in general a materials thermal conductivity will change according to the temperature, all right. This is a characteristic of the material, okay. But then if your analysis is only the changes of the temperature is very low, okay, meaning to say maybe the changes of temperature is about maybe 100 degrees Celsius, okay, let's say 100 degrees Celsius. Therefore, in that case, you can always just find one thermal conductivity at maybe at the average temperature. Let's say now the temperature range may be 25 degrees Celsius, okay, to 100 degrees Celsius, okay. So you just find any reference that give you a thermal conductivity in the range, maybe here the middle is 75, okay, let's say, all right. So if you can get around 50 to 75 or 80 degrees Celsius, that would be good, all right. Just assume it is constant throughout the changes of this temperature, all right. But then when it deals with applications where the process of your simulations take place, the temperature actually range from room temperature until it become melt. Okay, melting temperature. For a steel, the melting temperature will be 1000, maybe 800, it will be 1015, and so on. Okay, when that high range of temperature, then it would be better that you find temperature dependent thermal conductivity. Okay, meaning to say the thermal conductivity will change according to temperature. Okay, those software, commercial software, that allows you to put in temperature dependent thermal conductivity. Okay, so they in between then they will interpolate. Okay, interpolate the thermal conductivity. All right. Okay, so this is the examples of the temperature dependent thermal property of titanium 64. Okay, titanium alloy. Okay, where you can see that in the real experimental data itself, it could be several points only, right? Let's say this is the point. Okay, for thermal conductivity is the solid line, so let's say this is the one. Okay, so it could be your data consists of several points. Okay, it's okay when you enter into the FEA software. Okay, so what does FEA software? They will do an interpolations. Okay, within this range they will interpolate. Okay, with this range they will interpolate between these two. Okay, the software itself will do the interpolation for you. All right, to insert, let's say the temperature is 800, they will interpolate using these 2 points and put this temperature, this thermal conductivity into the equations and calculate. Okay, however, when it reach to the end, the software will just, they don't have another point to interpolate, then the software will just take straight line. Okay, similar to the end. Okay, they just take a straight line. This is a common interpolations method in the FEA software itself, right? So if in general, if you only give 1 point, therefore the software just treat it as a constant, okay, throughout the whole temperature range, right? Okay, so we can also interpolate for the A and so on. All right. Then also for a convection part, okay, since we start to deal with the real conditions, okay, even though our derivations is for the conductions, the convections come in as a boundary conditions. Okay, therefore you can always change or apply the convection or radiation as a boundary conditions to your control system or your control volume itself. Okay, so here again, this is a range, okay, of convection values, okay, generally 5 to 25, all right, for free convections, okay, of air. Okay, when you have a forced convection, it will be range from 10 to 500 and so on. Okay, so this value will give you an idea of what value to select when we consider a convections. Okay, if the convection is low, then we put 20, we can put 5. When the object involve higher temperature, okay, meaning to say there are higher convections, okay, then we could put a reason and select a higher value. All right, so these are the range, okay, that they have tested. All right, so it is very dependent on the experiment itself, okay, the experimental setup of the whole process. Okay, but for general analysis, okay, when we try to estimate, we just pick any value in this range, okay, with our reasons. Okay, that's all. Okay, until we have the opportunity to actually measure what is the actual convection value, then we could use our experimental value as our convection value, right? So this is how we can do it, okay, in the real situation. Okay, so this is one of these are the pictures, okay, extract from one of the paper, okay, by Professor Micheller's team. Okay, it is about modeling the force convection in the thermal simulations of a laser cladding process. Okay, laser cladding is just to add a material on top of we'll call this base as a substrate. All right, so it's a cladding process. Okay, so what they do is they actually develop several models, okay, how they can estimate the convections. Okay, so they have 6 cases how they make estimate the convections and apply it in the software, and they run one experiment. Okay, so this experiment is the temperature measured using thermocouple at different locations. Okay, it would be at this H, okay, this 3H, T, C1, 2 and 3, and then another one at the bottom of the substrate, right? So they would compare it with the experiment, and they conclude that in their research that certain methods, okay, would be better. All right, so in their case they would suggest do not ignore convections, okay, because convection still occurs, right? So you can see that whenever they apply a no convections cases, it is far away running out. Okay, the temperature, okay, the error itself is higher than the other methods. Okay, so this is just to validate. So as you can see, Professor Micheleris actually now he did his coding, all right, to develop a software, and actually his company has been bought out by the Autodesk, okay, and implemented as a NetFab fabrication simulations solver, right? And then beside that, we would have the heat source itself. Okay, so in the heat source itself, when we try to input the how would I say, when we try to input the energy, okay, to our systems, then we need a model, right? A mathematical model itself. Okay, we cannot simply put a value. All right, so this is important, especially when we deal with maybe a heat source given by a laser beam and others. Okay, so what we can do, okay, if there is equipment, then we can measure how the laser heat flux actually being distributed. Okay, some, in this case it is what we call top hat distribution. Some of the case it is in the Gaussian distributions. Okay, so it depends on the setting of the laser beam itself, right? So from there we can always model how this heat flux according to some established model. Okay, we just plug it in and we can start to model this shape, okay, into a mathematical functions, right? And this will be applied to the software itself. Okay, but then when we have a heat source, as we can see, when we derive this heat source, this is based on a common mathematical formulations. Okay, so these common mathematical formulations have a fixed constant. Okay, and there is a part where it includes this efficiency, or a constant where you need to tune or calibrate. Okay, why we would say is we need to calibrate is that if you have the experimental data, then you have to do calibrations to ensure that this is the actual value of heat flux, okay, or volumetric heat flux being applied to your system itself. Okay, otherwise if you don't have the experimental data, then you just estimate. All right, okay, based on the literature again, right? So this is how we can do a calibrations of heat source. Okay, we run a simulation similarly. Okay, we will find the bit profile. Okay, we find the width. In this case there is depositions, then there is a heat affected zone, okay, that we can measure. So from this is one of the important parameters or important informations that we can extract to actually identify the heat source, okay, profile, okay, to calibrate the heat source. So what we did here, we have did the experiment, okay, then we run the analysis and we compare, okay, between these two, okay. By comparing these two, we would find what is the actual setting, okay, that give us the closest to this, okay. So this heat affected zone, again, we can estimate it using temperature, okay, using a temperature, okay, from certain paper, okay. This heat affected zone is actually due to the temperature, and it causes the phase change of the material, therefore the color change, okay, and the behavior actually change, okay. Therefore we can do a relations between them, and from there we can calibrate accordingly. Then how we could apply it, all this heat transfer analysis, okay, maybe we go to a Q&A first, okay. If you have any questions, okay, we can discuss there before we move on to the applications, okay. So you can type in your questions if you have any. For the tutorial itself, whether you should submit or not, for now you don't have to submit it, okay, since you don't have that 20%, okay. But I still encourage you to try it, okay, because it is part of your exercise and it will help you in your test. Okay, so I think if you have any questions, you can still put in the chat and we will come back at the end of these sessions, right? So we move on to the applications, okay. So all these heat transfer simulations, how we actually use it in real situations, okay. In normal case, whenever we do an exercise, okay, or an assignments, okay, those assignments is already maybe a fin or whatever, it's already defined, okay. The problem is already defined there, okay. This is the shape of the fin and so on, okay. So in real case, we would apply it, okay, in the design process, okay. In that design process, we would want to estimate different things, okay. So if it is related to the fin, okay, the performance of the heat fin, the heat sink itself, okay, the fin of the heat sink itself, then you could apply it, okay, to find out what is the maximum temperature, okay, when that occurs, okay. Let's say the CPU increase to the run at the highest clock speed, okay. So what would be the steady state temperature, okay, by the fin, okay, and whether it is sufficient or not, okay. So you can change from there and you will see that if I increase the forced convection, okay, you adding a fan, okay, so how would that decrease the temperature, okay. So this will give you a rough idea of what could happens, okay, before you actually send the design for further experiments, okay. So this would be helpful, okay. So therefore that's why in the early stage, okay, you should estimate the thermal conductivity and other things, okay. Take into precautions that you should do a proper reference, okay, not simply put as any values it is, okay, as it, okay, so that your result should be more or less there, okay, before you run to your actual prototype and testing, okay. So now what we can also use is that we can estimate the effective thermal conductivity for a powder, right? Because in the solid itself, it's very obvious, okay, it depends on the thermal conductivity. But then when we talk about a powder, then how the powder actually transfer the heat from one powder to another powder, okay, this is one of the way, okay, that we can estimate, okay, what is the effective thermal conductivity for this powder, okay, to transfer, okay. So what we can do, we can generate or model a unit cell model, okay, and how it would be connected, okay, based on these connections, because when the temperature of the powder increase, then they will start to melt and sinter, okay, and join together, okay, to form this we call neck, right? So from here we would see how this neck change, okay, and what would be the thermal conductivity. All right, so this is the final elements model itself, okay, heat from one side, okay, going out from the other side. So eventually using this method throughout, using a thermal temperature dependent conductivity, okay, as well as the changing of the neck, okay, according to the temperature. Therefore we have successfully predict the thermal conductivity across a range of temperature until the powder being fully melt, okay. So we can see that the black dot, okay, it's actually when it come to a temperature where we estimate it's become a sintering temperature, where the powder start to form this connection, okay, form a lot of these connections, okay, at the neck. Therefore the temperature thermal conductivity now tremendously increase according to the temperature increase, okay. And this actually very closely match to the experiment being conducted by researcher Arch, okay, the square dot, okay. So we can somehow using this method to predict the effective thermal conductivity of the powder, right? Then also we can use the heat transfer analysis to investigate the influence of the process parameter, how it would affect, okay, on the thermal stress itself, okay. So in this research we would see that there is a depositions of material layer by layer, okay, and the directions of it, okay. So before we actually do the test, okay, we can do a simulations and see how it is, how the residual stress, okay, being induced inside the part itself, okay. So we could change with a different cooling process, okay, how it is changed in the time in between one layer with another layer, okay. So we can do all this investigation instead of doing the real testing and then do a lot of post experimental work, like cutting the specimen, okay, and then run it to another equipment to test the residual stress, okay. We can always estimate the residual stress, okay. This residual stress is the stress being induced inside the part, okay, due to the contractions and the expansion of the material, okay, during the heating and the cooling process, okay. So from there we can estimate the residual stress. At the same time also we can estimate the displacement, okay, of our specimen, okay. In this case we just take 2 point, okay, we measure this 2 point of the vertical displacement, and we did one experiment, okay, to validate that this whole simulations model is proper. All right, so we do measure this 2 point, okay, and we run the depositions, okay, and we found out it is very close, okay, to the experimental value, right, at different cooling point, okay. So this is a 40 minutes cooling process, right. Then also we can use it to optimize a process. As I mentioned, you can use it for fin or other process, okay, but those fin process are, I would say, they are static, right, in terms of the heat source, okay, because you attach it to a constant heat source, okay, unless in this case, whereas in this case the heat source is actually moving, right? So we can estimate how it change, okay, because the heat is keep moving, right? Therefore the behavior of the melting change, okay, so we model it, okay, using the heat flux equations that we have developed according to the equipment itself, right? We measure it and develop the model itself. Then we could estimate when the speed is low, what is the melting point, okay? This is the melting temperature range, okay, the gray area, where meaning to say when the heat source is being applied, this would be the depth of the melt, right? Then when the temperature increase, then the melting actually do not come to the baseline, okay, and then when further increase, then it becomes smaller and smaller, right? So we can see these changes, and from there we can estimate or optimize the process, okay, what is the parameter that we should put in, okay, to get the proper dimensions or melting, okay, across the two parts, okay. So this would be the one powder layer, okay. This is a adaptive process where you want to melt it so that it is attached to the other part, all right, and form a 3D surface. So therefore we could find a suitable range, okay, for it, okay. So this is a remelting process to make it with a better surface finish, okay. Generally, as I mentioned, there are steady state heat transfer, okay, and there are also in the previous few applications, this is a transient heat transfer problem, okay. So what are the differences? That in the steady state heat transfer problem itself, okay, the temperature at any particular point, okay, will remain constant when the equilibrium have been attained, all right, meaning to say no other changes, okay, after they have reached equilibrium, okay. So therefore the amount of energy enter in any sections, okay, will be equals to the energy exceeding that particular volume itself, okay. Therefore in that, when we run the steady state heat transfer analysis, the FEA software will actually run a conversion test, okay, to find out whether they have attained the equilibrium or not, okay. If not, they will continue to run, okay, until it reach the equilibrium, the temperature have been stable, and that would be our result, okay. Whereas in the transient heat transfer analysis, the temperature within the object keep changing over time, okay. For example, the previous one, okay, the heat source is moving, okay, therefore the positions and the temperature will change according to the positions of the heat source or the laser or the electron beam itself, okay. Therefore we would say the heat input, when we deal with the heat input and the heat loss that keep changing with time, then we should apply the transient heat transfer analysis in the FEA software, okay. You have to select the proper one, right? In this transient heat transfer, the temperature dependent convections, you can apply it, okay, because when the temperature change, then the heat loss also the rate of heat loss also change, okay. Therefore it become a transient part, okay. Then also when we involve a moving heat source and there are possibility of changing volume, okay, the volume change, like in additive manufacturing, the material being added, okay. In other applications, like one of my I would say another professor in US, they would run it to simulate a laser for maybe removing a material. Okay, so the volume of the material itself now changing. Okay, so it's either increase or decrease. Okay, so because of that we cannot run a steady state because it will affect the whole volume being stored and so on. Okay, when we run the transient analysis, okay, when we run the transient analysis, then we should aware of this guideline. Okay, so this is just a guideline given by Abacus, okay, where the time step or the time increment itself, okay, because we are doing a transient, meaning to say we will simulate from time 0 maybe to time 3000 seconds. Okay, so when we run this kind of transient analysis, we should identify what would be the next step. Okay, maybe this should be 1 second or maybe 0.1 second and so on. Okay, so the smaller it is, then your computer have to run many times, okay, until it reach the end of your analysis that you define. Okay, so in order to define this, we call it time increment or time step itself. Okay, you should based on this guideline. All right, so this is given by Abacus. Okay, but I have seen other papers where they write, when they use other software, they would put different value. Okay, Abacus recommends 6. Okay, I think 6 is good value. Okay, 6 is good value. Then in other software they would put maybe 12. Okay, it depends on how critical it is. Okay, but 6 is a good value already. All right, so the idea of having this guideline is that in the transient itself, the energy is being stored and transferred from one point to the other. All right, so therefore if you can see this rho C over K, okay, over K, the thermal conductivity is based on these equations. Okay, our main equations. So this part we move it over here. Okay, so divide by K. All right, so you can see that this would be related to the energy stored in the element itself. Okay, so in the transient itself, we should allow sufficient time for the heat being transferred to another node, okay, and being stored within the element itself. Okay, therefore we would suggest, the software suggests we should have this guideline. Okay, not too small. Okay, not necessarily the time increment is small, then we should get the good result, because in this case the energy may not be able to actually being stored. Okay, and because of being discretized, okay, therefore sometimes it will cause, we call it as a fake or maybe a false oscillations appear in the solutions, whereas the temperature, when they calculate according to the time, then it doesn't reach this point, therefore it stay on this point. Okay, it increase, then when it reach the other point, then this one suddenly decrease and so on. Right, so there is this kind of oscillations problem. Okay, so also in the commercial software itself, they allows us to do different kind of heat transfer analysis and relate it to the mechanical property. Okay, whereas we would say the thermal stress part. Okay, where we use the heat problem, and transfer it to the displacement part. Okay, so in Abacus, I think other software, they do have others similar name, okay, for this kind of problem. Okay, so one is the uncoupled heat transfer analysis. Okay, we just mainly do the heat transfer analysis. Okay, then there is another one is the sequential coupled heat thermal stress, meaning to say we would run the whole heat transfer analysis and then capture this temperature profile throughout the time, and we transfer it to run for the structural part. Okay, to obtain the stress, okay, the displacement and the stress of the part. Okay, then another one would be the fully coupled thermal analysis, means the software itself now will run it with the temperature increase, then they will calculate what is the actual displacement and other things, and then run again the heat analysis and do the stress calculations and so on. Okay, it's fully coupled inside the analysis itself, right? So this is one of the way of, I think we have discussed this before, how we can activate the elements for active manufacturing process, okay, where the heat source is actually moving from one point to another, okay, in a smooth point. Okay, so again, in this case, the selections of the time step is very important to ensure that the center of this heat source is actually matching to this point and the other point, okay, to avoid all this force problem and convergence problem. Okay, otherwise they will have a convergence problem and so on. Okay, so this is how it would looks like, okay, adding layer by layer and so on. Okay, so this would be the end of this part. All right, so any questions? I have also posted the attendance link in the chat box. You can always refer to that. Otherwise, you can go back to the Google Classroom and click the link there later on. Okay, so I think if we don't have further questions, we will end this sessions today, and make sure you try the tutorial, okay, and we would prepare for the test. Okay, there would be 3 tests. Okay, each test will be 20%. All right, 3 tests, each test 20%, and I would say each test will take you about 1.5 hours. Okay, so that it would be equivalent to like a final exam, 3 hours, 40%, right? So now it would be 2 tests to replace the final exam, which will be 1.5 hours. Okay, but it's better now we separate into 2 sections, okay, and 3 sections, sorry. Okay, right, so no more questions. We will end the sessions. Okay, there is one question. Is there any difference if we put an element for insulations or we put insulations at another face of the element? Put an element for insulations or we put insulations another I'm not really sure what this question asks, but generally I would say when you try to put insulations, okay, insulations is the physical part, okay, that you actually see or what you actually do in your experiment, okay, but mathematically in the finite element conditions, when we try to put the insulations, it is applying on the surface, okay, where you assume there is an insulations, and when we apply that one, there will be no heat being released, okay, meaning to say if we really put an insulations, we don't have to set anything, okay, meaning when we don't set anything, all those node, the temperature of the node will not decrease, okay, because there is no any mathematical functions applied to that node to let the temperature drop, okay, due to the convection or whatever it is. Do I need to specifically set up an element for insulation? No, it's just you select your element as usual, okay, but then you must select your insulation that contain the heat transfer formulation inside, meaning to say when you use Lisa or maybe Abacus or other software, when you select the elements, they specifically say this, what is the function of this element, they are for heat transfer or other things, okay. So you just have to select that elements for your heat transfer analysis, and then those insulations will be applied as a boundary conditions. Okay. Alright, so I guess no more questions. We will end these sessions. Okay, any questions, any further questions, do drop the message at the Google Classroom. Right, so stay safe and happy trying. Right, so see you again. Bye bye.